All right, let's continue this section on graphing quadratics. So, really quick, I want to review some vocabulary. The vertex was the minimum point of a quadratic graph, or the maximum point. The axis of symmetry is that line that divides the quadratic graph in half. The domain would be all the x values, not just one of the x values, but all the possible x values, and the range would be all the possible y values. And then we talked about this idea of stretching and shrinking. When something stretches, it's going towards the y-axis. It's called a vertical stretch because the y-axis is going up and down vertically, not horizontally. So when it's going closer, like this pink highlight one is closer, that's a stretch. But see how the red is further away? That's called a shrinkage because it's shrinking away from the y-axis. Okay, and I know it's next to, what's confusing sometimes is it's next to the x, but so people want to say horizontal, but it's actually a vertical stretch or shrink because it's in relationship to the y-axis. And then, of course, this idea of a parent function came up over and over again. And this is really worth writing down and memorizing. In fact, I went over it last video. And I probably should start at a -2, but that's okay. We have it on here. And this is worth remembering, that the parent function is f of x equals x squared, or it's a quadratic because it's to the second power, and it's a quadratic. And this is the parent function. This is what it looks like if we were to graph it, and everything else is going to be a modification of this. So this is worth knowing, right? And also another vocabulary word would be a parabola, and that's this U-shaped quadratic graph that we have. We call it a parabola. So I think we've covered it all, everything that we need to cover. And last class we went over the characteristics of a quadratic, and now we're going to, and then how to write those characteristics down. And now we're going to go over how to compare them. Remember I said we're going to compare everything to this. Now, standard form of a quadratic, let's see if I have it anywhere here. Yeah, standard form of a quadratic would be something like f of x or y equals ax squared plus bx plus c, where a, b, and c are actually numbers, and the x squared and the x are variables. That's standard form. That's the normal, it's the standard, right? Notice though, when we're talking about the parent function, it's just f of x, or you could think of it as a y if you want, equals x squared. We're not adding a bx yet, or a c, and right now when we're talking parent function, we haven't even added a number for the a. It's just a 1. It's an invisible 1. So today, when we're doing our comparisons, we're comparing everything to the parent function, so we're going to have to change it. And how we'll change it today is we'll add a number in front. We're still not going to add the bx or the c today. We're just going to add a number in front, an a, some number there, and we'll see how that changes it compared with the parent function. Okay, I've already said a lot, and that was mostly review, so let's get going. You can follow along in the textbook if it's a little blurry, because this part is a little blurry, even though I'll read it out loud. Okay, so now we're going to graph when there's an a in front of the parent function x squared, and you treat it different if the a is greater than 0, okay, than when it's less than 0. So we'll talk about that. And then when it says when 0 is less than a, which is less than 1, let me write that down because it's just 0 is less than a, which is less than 1. When that happens, well, what number would that be? What numbers would be greater than 0 but less than 1? Well, those typically turn out to be any number that's like a proper fraction where it's not over 1, right? This is a number that's greater than 0, less than 1, 1/3. 2/5 is also. Or you could write it as a decimal. See how this decimal is not quite at 1. It's not 1. It's less than 1, but it's greater than 0. So any number that's a fraction, we're not going to do too many decimals right now, just showing this. But any number that's a fraction that's less than 1, like 1/3 of 1, well, what happens? Well, that would be a vertical shrink of the graph, a vertical shrink. So a vertical shrink, I underlined in red, so you can see that in red, it's shrinking away, it's growing from, it's shrinking away from this y-axis, the y-axis. So if you have a fraction, it's going to actually be called a vertical shrink of the graph from the parent function, which I didn't color, I just left. The parent function is this gray one. If it's a fraction, it's going to be a vertical shrinkage. Okay, that'll be a vertical shrinkage. In case you can't read it, I know it's in your textbook, but I'll just write it down. It's called a vertical shrink. Okay, but what about if a is greater than 1? I don't think that needs any explanation. Any number greater than 1, like well, if you stay with whole numbers, it'd be like a 2, a 3, a 4, a 5,000. It's all those are greater than 1, right? What would that do to the graph compared to the parent function? Well, that is a vertical stretch. Vertical stretch. So if a is greater than 1, it's a vertical stretch of the graph. So you look at the parent function, which is this one right here. And an example of a vertical stretch would be this pink one. You see how it's stretching? It's like reaching towards this y-axis. That's why it's called a vertical stretch, okay? Any number greater than 1. All right, we're almost done, but I want to talk about when we have negative numbers. It's pretty much the exact same thing we just did, but it's almost like you put a mirror to it and it reflects down. And that's what it's called. It's called a reflection. So whenever there's a negative, you see when, in this case, this is when -1 is less than a or less than 0, it's a vertical shrink with a reflection of the x-axis of the graph. So again, we're reflecting on this x-axis here. Instead of going up on it, it's now going down. Okay, so that would be the comparison. And everything else would still be the same as far as the vertical stretch and the vertical shrink. Okay, so if it's a fraction, it's still a vertical shrink, which means it gets larger, but it's shrinking away from the y-axis. And if it's a number greater than 1, then it's a vertical stretch, which would be the pink here. Okay, all right. That was all theory and description. Sometimes we have a hard time just hearing it all without actually just seeing it. So let's see it, and then if you need to go back, you can. That's the cool thing about it. You can always go back. Okay. So it says compare the graph f of x of equals x squared. Well, that's just our parent function. If you recognize it, that's just the parent function. We've been using the whole time. This little thing, which is worth writing down. Compare that, which we did earlier last class. It looks like this, with this new one of 2x squared. Okay, so now the a is a number. And what number is that a? It's a 2. Notice that it's just the parent function, but there's a 2 now. It's just this x squared that we had, but now there's a 2 in front of it. Okay, so we're going to compare that. We're going to graph both of them and then talk about how they're the same as each other. Okay, so since I already had the parent function graph from last time, let's use that. Okay, so the parent function is already done. Remember, we just chose these numbers and we substitute numbers in, and now we want to graph this new one. Okay, so let's go ahead and do that. And I don't see another color marker. I do. I have a pink one. We'll use, I hope it's not confusing. I'm going to use the parent function's actually in black marker, and this new one's going to be in pink, but it's just so that you can see there's different colors. So we're going to substitute this -2 in and see what we get. Okay, so let's do that really quick. I have some paper right here. Oh, it's hard for you guys to see all of it. Let me scoot this over. Sorry, parent function. Ha ha ha. We're gonna graph this new one, and it's g of x equals 2x squared. It's a quadratic because there's this 2 there. Okay. So we're going to substitute numbers in, and the first number I'm going to substitute in is a -2. Well, why did I choose a -2? Just because there's no fractions here. It's just the first couple numbers you can try and still be symmetric. Okay. Okay, so a -2, let's substitute that in for an x. So their input's a -2. So 2 times, instead of an x, I'm substituting a -2 squared. Remember the order of operations. We always do the exponents before we multiply. So a -2 squared, well, a negative times a negative is a positive. It'd be a 4. But then you multiply. So if you input a -2, you end up with an 8. So if we input a -2, we output an 8. If we were to put in a -1, a -1 times a -1 squared would be 1. 1 times 2 would be 2. If we were to substitute a 0 in, we would have, maybe I should do it just so you guys see it. So I'll do it this one here. You can see I can do them in my head pretty easily. They're not that hard to do, because all you're doing is the power and then multiplying. 0 squared, 0 times 0 is 0, and that 0 times 2 would be 0. So if you input a 0, your output is a 0. What if you put in a positive 1? A 1 squared is 1. 1 times 1 is 1. That 1 times 2 would be 2. Oh, look, it's the same thing if I put in a positive 1, if I put a -1. I wonder if that will be the same. 2 times 2 is 4. 4 times 2 is 8. Great. So we're ready to rumble. And I want to show you, though, basically what I did here, okay? Because the steps here are going to be the same all the way throughout. Every time you graph, you're going to do these 4 things, which you should definitely write down. You're going to make a table, which is what I did. I made a table. You're going to plot, which is what I'm about to do. I'm going to plot these, and they're going to draw a curve smoothly through the points, okay? So these are the 3 steps that we need to do. I'll try to keep these to the side. Let me go ahead and graph this, and then we can compare it to the parent function. Okay, so let's graph it. If x is a -2, 1, 2, y is 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. If x is a -1, y is 2. If x is -1, y is 2. If x is 0, y is 0. If x is 1, y is 2. I'm saying y, but you know, it's whatever letter they tell us. It's g of x. So g of x is what they're saying this time. Same thing as a y. If x is a 2, y is 8. Or g of x is 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, it's going to be symmetric. So we did the first step. We made a table. We plotted these points. Now we draw a curve through those points and try to make it look smooth. Like anticipate how it would curve. There you go. Nice. Okay, so then it said compare these two. That's not too hard to do. Let's compare them. Well, how does this one compare the pink one with the parent function? Well, it looks like they have the same axis of symmetry. It's the same, right? If you were to divide this down the middle, it would still be the y-axis. Or another way to say it is that y equals 0. Okay. If you were to ask what the vertex is, what's the vertex? The vertex is still the x is 0. Whoops. And y is 0. The x and the y are both 0. It's just at the origin here. So they have the same vertex. I would say the axis of symmetry and the vertex are the same. Okay. But is it a stretch or a shrink? And that's the part I want you to think about. I'll give you a second. So remember, it's a whole number. It's not a fraction. So when we have a whole number, are we stretching towards the y-axis? Are we shrinking away? Well, actually, you can visually see it, right? Here's the parent function. Is it stretching towards or shrinking away? Is it going towards this y-axis or going away from it? So what do you think? Give a second here. Yeah, it's obviously stretching towards, right? So there you go. All right, excellent. So We did one with out of fraction. We just did a regular type problem. We have one more to do, and I'm thinking that this video is going very long. So let me stop it here, and maybe we'll hit this one on another day. All right, sounds good.